Hello, UMTYMPers. Welcome to section 13.1, Mathematical Induction. Mathematical induction is a proof technique that you can use when you're trying to prove something about all the natural numbers. It is probably my second favorite proof technique. It's pretty cool. It feels super powerful because you can just prove all of the things. So to get started, I want you to try to find a formula for the sum of the first n odd natural numbers. Pause the video, give it a shot. All right, cool. So probably what you did is you were like, well, the first two odd natural numbers sum up to this, and then the first three sum up to this, and then the first four sum up to this, and you tried to find a pattern. And that's a good way to start. What about this guy? What about this question here? What's bigger, 2 to the n or n plus 1 squared, where n is a natural number? What do you think? Pause the video, try to work it out. All right, welcome back. Again, probably what you did is you said let n be 1, and then you did 2 to the power of 1, and then you did 1 plus 1 squared, and so it was bigger, and then you said let n be 2, let n be 3, let n be 4, and so on, and tried to figure out which expression was bigger. Here's the thing, though. It doesn't matter how many different values of n that you try out. You can't try out all of them. What trying out a bunch of n will do is help you formulate a conjecture. And conjecture may or may not be true. In math, we have to prove our conjectures in order to be certain that they're true. Here's a proof from Euler. I'm going to read it to you. I think it's pretty cool. The kind of knowledge which is supported only by observations and is not yet proved must be carefully distinguished from the truth. It is gained by scientific induction, as we usually say. Yet we've seen cases in which mere scientific induction can lead to error. Therefore, we should take great care not to accept as true such properties of the numbers which we have discovered by observation and which are supported by scientific induction alone. Indeed, we should use such discovery as an opportunity to investigate more exactly the properties discovered and to prove or disprove them. In both cases, we may learn something useful. So scientific induction is when we look at a bunch of cases and we try to come to a conclusion from those cases that we look at. Scientific induction does not rise to the level of proof in mathematics. We can't just look at a bunch of examples. We have to show it for all cases. So how do we prove this for all cases of n? We can't do all the natural numbers. There's infinitely many of them. Enter the principle of mathematical induction, not scientific induction, mathematical induction. Here's how your book talks about it. So the idea behind mathematical induction is you start with the first case. It's usually for n equals 1. So you take whatever it is that you're trying to prove and you prove it for n equals 1. Okay, I call that the base case. People call it different things. I call it the base case. So for n equals 1, you prove it. And then what you do is you assume, well, there's strong and weak induction, but that's irrelevant. You assume that the statement is true for some natural number k. And then you have to prove that if it's true for k, then it also must be true for k plus 1. And what that allows you to do is any point on this ladder where you are, that step allows you to take the next rung on the ladder. So the base case gets us on the ladder, and then the inductive step allows us to go from any rung of the ladder to the next rung. And that gets us all of the natural numbers. So that's the principle of mathematical induction. Easier said than done, but this is the idea. Here, I'm going to do one for you. So this statement here is the one I asked you about at the beginning. What's the sum of the first n natural odd natural numbers? We're going to prove that it's n squared by mathematical induction. Okay. The first thing we have to do is prove that the base case is true. The base case is this equation 1 plus 3 plus 5 dot 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 up to 2n minus 1 equals n squared when n is 1. Okay, so if I plug 1 in for n, the right hand side is 1 and the left hand side is 1. 1 equals 1, so the base case is proved. Done the base case. Then I need to do the inductive step. I assume that the statement is true for some natural number k. And then I have to show that this is true for the next natural number, k plus 1. Writing that out in symbols, here you go. I just took the thing that I'm trying to prove and stuck k plus 1 in instead of k. That's all I did. By assumption, we know 1 plus 3 plus 5 up to 2k minus 1 equals k squared. I know that for sure. That's what I'm assuming to be true. Therefore, a bunch of algebra. This is a bunch of algebra. What did I do? I just added this term 2 times k plus 1 minus 1 on the left and right hand side. Why? You'll see in a second. And that's just the next term in the sequence. So what I'm trying to do is make my assumption here look like what I'm trying to prove here. That's it. So it's close, but not quite. Do a little algebra on the right hand side. Do a little more algebra on the right hand side. Do a little factoring on the right hand side. And that's exactly what I wanted. There it is. I assume that the statement's true for k, and now I have shown that it's true for k plus 1. I've shown the inductive step. This means for any rung on the ladder, I know how to get to the next one. So, by principle of mathematical induction, the sum of the first n odd natural numbers is n squared. I'm going to end the video there.